Welcome back to the video series on integration and differential equations. In today's video, we're going to look at the situation where the auxiliary equation has repeated roots. If the auxiliary equation has repeated roots, then the general solution to the DE looks like this. Y is going to be a polynomial times an exponential. The particular root m that is being repeated is going to go into the exponent of the exponential alongside an x. And if we take a look at this polynomial here, there will be one term for each occurrence of the root m. Here's our first example. We want to solve the following DE. This DE is a homogeneous DE with constant coefficients. So let's recap what that means. Homogeneous refers to the fact that we've got 0 on the right side. A non-homogeneous DE would have a function of x or a constant on the right side, but in this case we've just got 0, so homogeneous DE. And constant coefficients refers to the fact that on the left side we're just seeing constants 1, 6, and 9 as the coefficients. We're not seeing any functions of x or y as the coefficients here. So that tells us that it's valid to set up the auxiliary equation. Y double prime is going to become an m squared, the y prime becomes an m, and the y term becomes the appropriate constant, so it's going to become plus 9. And that's equal to 0. So we can solve this equation here either by factoring or by the quadratic formula. In this case I would factor because this is a perfect square. This is m plus 3 all squared. We're setting that equal to 0. And in looking at the solutions, there are two options. M could be -3 or -3. So we've got a situation where our root is repeated. The root occurs twice. So let's see if we can follow the formula over here and write down our general solution. Y is going to look like c1 plus c2x times e to the -3x. So in the exponential we've got the form e to the mx. M is our root, so in this case it's -3. And notice that in the polynomial part we've got two terms because our root occurs twice. So I've recopied the form of our general solution in case we want to take a look back at that. And let's try a second example. Again, we've got a homogeneous DE because we're seeing a 0 on the right side here. On the left side we do have constant coefficients. So that tells us that it's valid to set up the auxiliary equation. It'll look like m cubed plus 10m squared plus 25m equals 0. Before trying to factor or use the quadratic formula, we want to ask whether there are any common factors that can be pulled out of all these three terms here. And the answer is yes, there is an m that could be pulled out, so that will help us with our factoring. We'll pull the m out, that will leave us with m squared plus 10m plus 25. That's equal to 0. And then now this quadratic here is a perfect square, so we can factor that as m plus 5 all squared. Great, so that is equal to 0. Alright, so let's see if we can write down our different roots. The factor m will be 0 if m is 0, so that's one of the options. And then from the m plus 5 factor, we're getting the solution -5, and that root there is repeated twice. So m equals 0, -5, -5 is the complete list of roots. Okay, now let's see if we can write down our general solution. So we've actually got a multi-concept situation here. The root m equals 0 is not repeated. So we're just going to refer back to our basic idea of distinct real roots that we talked about in an earlier video. And the term associated with m equals 0 would look like c1 e to the 0x. Okay, now in a completely independent way, we're going to deal with the root -5. So now what's going on with -5? That's a repeated root. So we're going to have an appropriate polynomial times e to the -5x. And since -5 is repeated twice, we want to have two terms in that polynomial. Okay, so the correct thing to write here would be c2 plus c3x. I would just really make a point of saying watch the names of the constants because it is easy to get mixed up here. You want to make sure that you haven't used the same name twice. So we've used C1, C2, C3. We've named them correctly. And we've made sure to use two terms here associated with the root m equal -5. So a couple more comments about how to write this solution. First of all, e to the 0x is just 1, so we don't really need to write that down. So a good final answer would look like this. And then the second thing I would point out is that there really is no convention for the order in which you write the terms. So maybe you would have found it easier to deal with the repeated root first. We could have said c1 plus c2x times e to the -5x. So that deals with the -5s. And then we'd move over to the root 0 and we'd say plus c3 e to the 0x. And then that exponential then just simplifies to 1. So we would erase it. So that's another good final answer. In each case, we've used the appropriate constants c1, c2, c3, and we've obeyed the proper form for the general solution. Final problem for this topic. Let's solve the following dE. Again, it's a homogeneous dE with constant coefficients. So we can set up our auxiliary equation. And I would point out that the notation here, this is just alternative notation for the derivative. So this term here represents the fifth derivative of y, and when we create the auxiliary equation, we'd be writing m to the fifth. So m to the fifth minus 4m to the fourth plus 4m cubed is going to equal 0. And before we factor, let's think about pulling out a common factor from each of these terms here. So we could pull out a power m cubed from each of these terms, and that would leave us with m squared minus 4m plus 4. So that's already looking a whole lot better, and that's equal to 0. So again, we've got a perfect square. That quadratic is m minus 2 all squared. That's equal to 0, and we can now write down our roots. So in looking at this m cubed, you could think of this as really m times m times m. So that reminds us that whatever root there is here is going to be repeated, and the correct root is 0. So we've got 0 repeated 3 different times as a root, or it occurs 3 times as a root. And then we've got the root positive 2, and that occurs twice. So overall, 5 different roots. And that makes sense if we're solving a 5th degree equation. So exponent 5 there in our equation, then we expect to have 5 different roots in the answer. There we go. So 5 different roots. 0 is repeated 3 times, and 2 is repeated twice. So let's see if we can write down our general solution. Okay, let's start with the root 0. So we'd have c1 plus c2x plus c3x squared times e to the 0x. And now that we've written that down, we can say, well, we don't really need to write down that exponential because it's just going to be 1. So I'm going to erase it. So that takes care of the roots that are 0, and then we need to move on to the roots that are 2. So we're going to have a certain polynomial times e to the 2x. And this polynomial here is going to have two terms, because 2 is repeated twice. Okay, now the only catch here is just to be a little bit careful about the names of the constants. We've already used the names C1, C2, C3, so we should call these constants C4 and C5. So C4 plus C5x would be the correct polynomial there. Alternatively, another person might have handled the roots in the other order. So another equally good answer would have been to say C1 plus C2x times e to the 2x plus C3 plus C4x plus C5x squared. Both good answers, just different ways of expressing the same thing. Thanks for watching, and we'll see you in the next video.